Today we're talking about nonparametric regression. And in the context of the course, it sits here. We've talked about linear and logistic regression. Really, these are sort of a subset of what we're going to be talking about today, which is regression a little bit more broadly. And if you remember, the idea, as we've talked about for regression, is we're just trying to estimate this conditional mean function. And if we had the whole joint distribution between x and y, we could just read that off by taking this expectation. But unfortunately, we don't have the population. What we have is a sample. And we need to use that sample to estimate this conditional mean function. The reason we would want to do that, of course, there's many different reasons. We could simply want to know, is there a pattern between x and y? And what is that pattern? Is there any kind of association? We don't really care about predicting y from x. We don't care about y. Y, not the letter y. That pattern is there. We just want to know what is the pattern. Or we could care about prediction. So if I have a new value, so somebody comes into the clinic, they have a particular age and a particular set of comorbidities. I want to know what's the probability that they will develop a more severe form of their disease within the next 5 years, because maybe there's something that we can do about that if we know early. Or maybe we're interested in a causal question. So if I change one of these predictors by some amount, if I could somehow intervene, what would the effect of that be on the average outcome in the real world? So that's all reasons why we might need such a conditional mean function. For this case, we know that's because of this identification result. Now, the problem is that if we're using linear models or logistic models, we're very limited in all of those, because the linear and logistic models are making these strong parametric assumptions. And the reality is that the data, or the population relationships, are almost never linear. They're almost, variables are almost never normally distributed. So we know that we can get away from some of these. Like if we use the robust standard error, that's a bit better. But these assumptions are still going to bite us, and they bite us in different ways. So for description, if you're doing linear regression, you may not pick up on nonlinear patterns. So for example, if the relationship between y and x is a U shape, then if you fit a linear regression, we're going to see this in a minute, you're going to get a flat line. And you're going to get a flat line with very high confidence. You're going to have a lot of stars on that regression coefficient, tiny p-value, very small confidence interval. It says there's nothing going on here. Now, of course, you shouldn't interpret that to mean there's nothing going on. You should interpret that to mean that the best fitting line is flat. That doesn't mean that the relationship is actually a flat line. It could be a U shape, right? But that means that, okay, if you're trying to interpret that descriptively, that's obviously very limiting. Now, what about for prediction? Well, for prediction, let's say that we fit a linear regression here. Let's say the linear regression fit we get is that. We can see, for example, for this guy here, if I had instead fit this regression model, somehow fitting a curve, the error would be a lot lower with that regression model than with this linear regression model for really the majority of these points. There may be some where this line is the line is fitting better than this curve, but for most of the points, the curve is doing better. And so if you're trying to ascertain risk, or what's the most likely outcome for patients in a clinic, or for people who are insured, who's going to drop off insurance, who do we need to offer services to, that kind of stuff, then you're going to do a lot worse by using linear or logistic prediction models than you would if you somehow had some way to fit these nonlinear relationships automatically. Similarly, for causality, we know that the identification result that we have depends essentially on knowing the true conditional mean. And so then the problem is, how well can we estimate the conditional mean? So even if we have this identification result, we measure all the confounders that we need, where we feel pretty comfortable about really whatever thing is unmeasured is only introducing maybe a little bit of bias. Well, we can still mess it up if we don't estimate that conditional mean very accurately. And if, for example, if we fit linear regression, and really the relationship is nonlinear, we have bias that comes from essentially excluding you can think of the nonlinear part of those variables as unobserved, because we're not including it in the regression model. So that's kind of, we've added in unobserved confounding by not adjusting for that nonlinear part. So that is bad. And that's why we would, if we're doing causal inference, we really want to have methods that can fit these nonlinearities without always having to automatically specify what they are.